Let's consider how we might be able to locate the zeros of a polynomial function numerically. Let's consider h of x equals 2x cubed minus x squared minus 4x plus 3 that we investigated earlier and whose graph is shown below. First, we find each pair of function values in the table and answer the questions that follow. In the first box, we are asked to find h of negative 2 and h of negative 1. When I substitute negative 2 into the polynomial function, I get an answer of negative 9. This represents the point negative 2, negative 9 on the graph. This point will be clearly below the x-axis. When I substitute negative 1 into the function, I get a positive value of 4. That represents the point negative 1, 4 on the graph, which we can kind of see here. The point is, when the x value is negative 2, the point is below the x-axis, and at negative 1, the point is above the x-axis, which tells me that somewhere in between, it must have crossed over the x-axis, given this is a continuous function like a cubic function generally will be. Let's take a look at the next box, h of 0 and h of 2. When I substitute 0 into my function, I get a positive value of 3. 0, 3 represents a point above the x-axis, which you can clearly see on the graph. When I substitute 2 into h, I get 7, another positive value. That point is not quite on the graph, but you can see how it would be if we extended this graph a little higher. So between 0 and 2, the y values are both positive. So you might be inclined to think that, well, there must not be a 0 between 0 and 2 because they're both positive. But there actually is a 0 between x equals 0 and x equals 2, and that's the number 1. So what does this tell us? Well, first of all, since h of negative 2 is less than 0 and h of negative 1 is greater than 0, then the graph passes through the x-axis at some x value between negative 2 and negative 1, which I mentioned earlier. But as for the second example, since h of 0 is greater than 0 and h of 2 is also greater than 0, then no determination of the existence of a 0 between 0 and 2 can be made. Now, we can see from the graph that there is indeed a 0 between x equals 0 and x equals 2. But if we were just looking at it numerically and did not have a graph to look at, we would not be able to determine yes or no that there is a 0 between these x values, because the y values are the same sign. The main idea of this section is to know that if the y values change signs, then you know that somewhere between these 2 points there is a 0 of some kind, and we've narrowed down where it is. Based on what we have just seen, what inference can you make about the existence of a 0 of a polynomial function if you know the value of the function at 2 different x values? So here is our theorem that we're interested in. It's called the intermediate value theorem. And it says, if f of a and f of b are opposite signs, then the graph of f of x must cross over the x-axis at some x value between x equal a and x equal b. Thus, we can say that there exists a 0 between a and b with odd multiplicity. Odd multiplicity because we know with even multiplicities, it won't actually cross over. It will just be tangent. Let's look at this next example. The table of values below represents values of a quartic function. Remember, that's an x to the fourth power. That means we could have as many as 4 zeros. The function has a negative 0 and 3 positive zeros. Answer the questions that follow. Is or are there any of the zeros of f of x specifically identified in the table? And what is the multiplicity of this zero? Explain your reasoning for both questions. So let's first look for a zero in the table. A zero is where the y value is 0, a point on the x-axis. So this point right in the middle of the table, 1, 0, is a 0. Now, the point to the left of it, 0, negative 3, is not a 0. This is a y-intercept, and we're interested in x-intercepts. Since f of x equals 0 when x equals 1, then x equals 1 is a 0 of f of x. So that is explicitly shown in this table. Of the 4 possible zeros, we've found one of them. It's a positive 1. Now we're supposed to guess at the multiplicity of this 0. And we can do that by looking at a point just to the left of this 0 and just to the right of it. Notice that just to the left of this 0, the y value is negative. And just to the right, the y value is also negative. That must mean that this graph comes up from the negatives, touches at 1, and then goes back down into the negatives. And I've said that in this paragraph here. Since f of x is less than 0 on the left of 1, 0, and f of x is greater than 0, that is not true. I should say less than. Fix that. Less than 0 on the right of 1, 0, then the graph must be tangent to the x-axis at x equals 1. Because it's negative on both sides, it doesn't cross over. This must mean that the 0, x equals 1, has an even multiplicity. This is a quartic function, 4th degree, with other zeros. So the multiplicity of the 0 is 2. In other words, it's not 4. Any even multiplicity would do this tangent bounce off the x-axis. So we have our 1, 0 with a multiplicity of 2. We're going to find other zeros. Between which two x values in the table is the negative 0 located? Well, let's look over here at negative x values. Notice when x is negative 4, the y value is positive. But when x is negative 1, the y value is negative. This must mean that the graph somewhere between x equals negative 4 and x equals negative 1, it crosses over from the positive y values into the negative y values. So somewhere between these 2 points is a 0. And so that's explained here. Since f of x at negative 4 is greater than 0, and f of negative 1 is less than 0, then there exists some 0 between x equals negative 4 and x equals negative 1. So while we don't know what it is exactly, we know we've kind of narrowed down where it might be. The third question says, between which two x values in the table is the second positive 0 located? Let's go back and look at the table. Over on the positive x values, 1, 2, 3, 4, 5, 6. Notice where the y values change. When x is 3, the y value is negative 5. It's a negative number. This point is below the x-axis. But when x is 5, the y value is positive. That's above the x-axis. Again, somewhere between these 2 points, it crosses over. Since f of 3 is less than 0 and f of 5 is greater than 0, then there exists some 0 between x equals 3 and x equals 5. So we can use this intermediate value theorem to help us narrow down and locate where the zeros might be.